Assalamu alaikum, sir.
Assalamu alaikum. So we had started talking about order of reaction, and I told you that the reaction depends on the concentration of the reactants. Like you've got X bumping into Y. So the more concentrated the particles, the higher would be the collisions. There would be more frequent collisions, and the reaction would kind of speed up. But not always. I mean, there would be other factors as well. We're going to discuss those. So the rate of the reaction depends on the concentration of the reactants. They depend on the concentration of X and the concentration of Y. So if any one of the concentration goes up, the reaction would kind of speed up because there's going to be a lot more collisions. Except that we don't know how it's dependent on X and Y. So it all depends on the powers A and B. So that's known as the order of the reaction. We talked about zero order, we talked about first order, and we talked about the second order. Now, zero order was that if rate is dependent on the concentration of X and it has a power of 0, that means that what it simply means is that it's not dependent on the concentration of X. Like no matter how much you change the concentration of X, the reaction is not going to speed up. Nothing would happen to it. Because if it's power 0, that means you put any value over here, whatever the concentration of X is, power 0 means that it's going to come out to be 1. So the rate would remain kind of unaffected by whatever the concentration is inside these brackets. Similarly, if rate is dependent on the concentration of X and the power is 1, that means it's a linear relationship. And what that means is that if you double the concentration of X, then the rate would also kind of double. So you decrease the concentration of X, the rate would also decrease. And then you're going to have a quadratic relationship, which is order 2. Order 2 is that you change. So that means rate is, it's the dependence is a lot. You change the concentration of X, the rate would not increase or decrease proportionally. It's going to, like if you double X, the rate would quadruple. If you triple X, the rate would become 9 times. If you decrease the concentration by half, the rate would become 1/4. So that means the rate is kind of more sensitive to the concentration of X. So the thing is that that the relationship is not always linear. Sometimes it's not dependent. Sometimes it's too dependent on the concentration of X, and sometimes it's going to be a linear relationship. So why do we have different orders? That's the first question. So it all depends on the mechanism of the reaction. So it depends on the mechanism of the reaction. Now, reactions don't simply happen that it's not that just the two particles that are just bumping into each other. So that's an overly simplistic view of a reaction. Like I just showed you that if X and Y are reacting, I just showed you that X is just bumping into Y, and that gives you Z. Reactions are not that simple. A lot of reactions, they involve a lot of steps. Maybe there would be intermediates being formed. X reacts with Y, produces something W, and then W reacts with X again to form Z. So reactions have multiple steps, and so which complicates things. So it depends on the mechanism of the reaction. Now, one of the reactions that you've already studied is an SN1 mechanism of a tertiary halogenoalkane. So right now, if you don't remember, I'm just going to write down the mechanism of the reaction. The reaction is simple. It's just a tertiary halogenoalkane that reacts with a chloroalkane. It reacts with OH ions. And what happens is that the Cl ions, they get substituted. And OH takes their place. So it's a simple reaction. And you've got two reactants. You've got your reactant. Just hold on one second. So this one, it's just a second. Okay, anyways, so it's not just OH minus one. Can you all hear me?
Yes.
So it's not just OH minus one bumping into CH3, this halogenoalkane. The reaction is not that simple. This reaction, SN1 mechanism, has 2 steps. What happens is there's a step 1, and in step 1, what happens is in the first step, the halogenoalkane, it kind of dissociates or breaks down into a carbocation. So this CH3Cl, it breaks down into, I say it breaks down into a carbocation and a Cl minus 1. So just hold on 1 minute for the azan. Just going to write the mechanism. So let's continue. So I was just telling you that mechanisms are not that simple. Most reactions happen in multiple steps. And what happens over here is, in this particular case, what's going on is that the Cl breaks away first, and then in the next step, OH joins up. Now, the Cl breaking away first is a very slow step. It requires a lot of time. The Cl is not just going to break away. It would require a lot of collisions. So it's a time consuming process. But once the carbocation is formed, the OH minus one is very quickly attracted to it. So this one is your fast step. So what you can think of this as, let's give them values. Let's say the slow step is taking 100 seconds and the fast step is taking just 1 second. I mean, the fast step is very fast. The positive ion and the negative ion would be very, they would attract each other very, very quickly. So you've got two reactants. Overall, the reaction is, I mean, the two steps are combined and the overall reaction is you've got a halogenoalkane and OH ions. These are your two reactants. Now the OH ion is involved in the second step and the chloroalkane is involved in the first step. So both reactants, reactant number one and reactant number two, they are appearing in different steps. So if I were to increase the concentration of OH ions, which step would increase in speed? Can anyone tell me? Like if I increase OH ion concentration, anyone?
Step 2.
Number 2.
Okay, so if I were to add more OH ions, then there would be no effect on the first step. I mean, the first step would be unchanged because OH ion has nothing to do with the first step. Step number 2 would speed up. So let's say I increase the concentration of OH ion and the reaction speeds up 100 times. And now it's taking 0.01 seconds. And I've increased the concentration of OH ions by a lot. Like if I increase the concentration like 1 million times, the reaction really, really speeds up and it takes like 1 microsecond. But do you think, would there be any large effect on the overall speed of the reaction? Like what happened to the overall speed of the reaction? It was taking 100 seconds for the slow, 1 second for the fast. So the overall speed of the reaction was 101 seconds, right? Now, even if you increase the concentration of OH ions by 1 million times and this fast step, it decreases in speed and takes 1 microsecond, the overall speed of the reaction is still not going to come down below 100 seconds. I mean, it's going to, like you keep on increasing the concentration of OH ions, the reaction at best would reach 100 seconds. Is this point clear?
Yes, sir.
Is this clear to everyone? Lubena, is this clear?
Yes, sir.
So the point is that OH ions, they don't really matter. I mean, that's order 0. Like, I mean, they almost don't matter because the step that they are trying to increase, it's already very fast. So even if you try to increase the concentration of OH ions, pretty much almost nothing would happen. Like you're just wasting your effort. You're just wasting OH ions. Like, I mean, there's no need for adding so many OH ions. Your reaction speed is hardly going to be affected. But on the other hand, if there's a halogenoalkane and you try to increase the concentration of the halogenoalkane, now which step will increase in speed?
The first.
Okay, so the first step. So I double the concentration of halogenoalkanes. The collisions double and the reaction speeds up, and and when the reaction speeds up, the time decreases by, let's say, 50 seconds. Now, all of a sudden, your reaction went from 101 seconds to 51 seconds. So that means the overall rate of the reaction or the speed of the reaction is just dependent on one of the reactants. The other one is barely doing anything. So is this clear that why the orders are different for different reactants?
Yes, sir.
Yes, sir.
So the basic idea is it all depends on the mechanism. Reactions happen in many different multiple steps. They don't just, whenever you see an overall reaction, that's just an overly simplistic view. In organic chemistry, you've studied that every reaction has a particular mechanism and it has different steps. So an overall reaction, you don't really get a lot of information about the order of the reaction. I mean, the overall reaction is pretty much meaningless when it comes to calculating the order of the reaction. You need to look at the mechanism. That's what's going to tell you. The mechanism is going to give you an idea of the order of the reaction. So the idea is, who's going to be order 0? Order 0 is going to be any reactant in the fast step. I mean, that reactant is almost irrelevant to the speed of the reaction. You try to increase the concentration, the speed will increase of the fast step, but it doesn't really matter at the end. Like, I mean, if 1 second takes 1 microseconds, the overall speed hardly gets affected. So who's order 1? Order 1 is, it's any reactant that's in the slow step. I mean, that's a simple thing. So what is meant by order 2 now? How do you get order 2? Like, why does a reaction become so sensitive to a particular reaction or reactant? Like, you double the concentration, it becomes 4 times. Now, order 1 makes sense, order 0 makes sense, but how do you get order 2? Now, for order 2, I would have to, let me find a suitable mechanism. TK, where's reaction kinetics? This one. So just a second, let me find this one, probably this one. Just give me 1 second. It's going to take some time to find. So let's, I think we should do CLO NH3. You forget this. Just once again, let me. So this one is a 4-step mechanism. Yeah, I actually forgot where the example was. Just a second. Not this. This one. I finally found this. So I'm going to copy this. And I wanted to show you how do we get order 2. So for order 2, I have this reaction scheme. And it's got this overall reaction. This is the reaction that's happening. It's the 3 reactants. So the 3 reactants involved. And there's H2O2, there's 2I minus 1, and there is 2H plus 1. So the reaction is going to be, dependent on all 3 in some way. Maybe it's order 0, maybe it's order 1, order 2. So it's got these 3 steps. So how do we get order 2? So remember, the rate of the reaction depends on the slow step, not on the fast step. So let's assume that step 1 is very fast. And step 2 is also very fast. And the third step is our slowest step. So the rate of the reaction depends on these 3 reactants. Okay, this is what we just learned, that the rate of the reaction depends on this slow step. So it depends on the concentration of HY. It depends on the concentration of H plus 1. And it depends on the concentration of I minus 1. I mean, let's assume that the first fast step takes 1 second. This one takes 1 second. So it's kind of pointless to actually speed up the fast step. And your slow step takes 500 seconds. So by changing the concentration of HY, H plus 1 or I minus 1, you speed up the slow step. That's why the overall reaction speeds up. Right? Is this clear so far? This part?
Yes, sir.
So your rate depends on these three reactants. But if you look carefully, I mean, HY is, I mean, you have H plus 1 as the reactant, you've got I minus 1 as the reactant. The third reactant is H2O2. So where did HY come from? I mean, there is no HY in the reaction. HY is an intermediate. So HY is actually formed in the previous step. And HY is formed when IO minus 1 and H plus 1 react. So when I say that rate of reaction depends on the concentration of HY, that kind of, just one second, what's the... So Adam, I'm just saying that it's the slow step. I just assumed that it's the slow step. I mean, I don't know if it's the slow step. I just called it the slow step. Is this clear? So I'm just assuming that that's the slow step. No logic behind that. So coming back to HY, remember HY is not your reactant. So when I say that rate of reaction depends on HY, so where did HY come from? HY was made in step 2. And HY is dependent on H plus 1 and IO minus 1. That means if the concentration of IO minus 1 and H plus 1 is high, then the concentration of HY that is formed would also be high. So HY depends on H plus 1 and IO minus 1. So when I say that rate depends on HY concentration, what I actually mean is that rate depends on the concentration of, indirectly depends on the concentration of I minus 1 and H plus 1. Because HY is just an intermediate. So when I say that rate depends on this thing, the concentration of HY itself depends on H plus 1 and IO minus 1. If their concentration is high, then HY concentration would be high. If their concentration is low, then HY concentration would be low as well. So whenever there's an intermediate involved, the intermediate itself is dependent on two other things. So that means rate is indirectly dependent on these two things. Is this point clear?
Yes, sir.
Is this clear to everyone? Ethan, Mob, is this clear? Minail, clear? So the next part now is, now I've removed HY. What I'm basically saying is that rate is indirectly dependent on IO minus 1 and H plus 1. So it's now dependent on four things. But again, now there's a problem that I'm saying that rate depends on IO minus 1. There is no IO minus 1 in the reactant. So where did IO minus 1 come from? So when I say that rate depends on IO minus 1 concentration, IO minus 1 itself was formed in the previous step. And its concentration depended on the concentration of H2O2 and I mean, they reacted to form IO minus 1. So when I say that rate depends on IO minus 1, what that basically means is that it's indirectly dependent on H2O2 concentration and I minus 1 concentration. Because when I say that rate depends on IO minus 1 itself is made in the previous step, and its concentration depends on these two things. So in that way, rate depends on all of these things. Initially, I said that it depended on these three things. Then I found out that HY itself is made from these two things. So rate indirectly depends on these two things. Then I found out that when I say that rate depends on IO minus 1, I figured out that IO minus 1 itself is dependent on I minus 1 and H2O2. So that means instead of writing IO minus 1, I'm going to write H2O2 and I minus 1. So is this clear, this expression?
Yes.
Yes.
So if I sum this up, that means rate is depending twice on H plus 1 over here, and it's again dependent on H plus 1. It's also twice dependent on I minus 1. It was dependent on I minus 1, and it's again dependent on I minus 1. So that means if I sum all of them up, it's dependent on H2O2 concentration, it's dependent on H plus 1 concentration twice squared. I minus 1 concentration, that would be order 2 as well. So that's where power 2 is coming from. And what that basically means is, I mean, the first thing that you should take away from this is that whenever there's an intermediate involved, trace that intermediate. I mean, that intermediate would be dependent on other things. And if there's another intermediate, then trace that intermediate. That intermediate would be dependent on other things. Okay? So when you say rate depends on HY, that means it's kind of depends on H plus 1 and I minus 1. And when you say rate depends on I minus 1, that kind of means that it depends on I minus 1 and H2O2. So is this clear?
Yeah.
I said then,
Yes.
okay, so then why is it order 2? Why is it so sensitive? I mean, we've traced it back. We figured out that it is going to be order 2. So now the question is, why is the rate increasing by a quadratic function? Like if you double H plus 1, why does it quadruple? So let's focus on H2O2 first. If I increase H2O2 concentration, what happens? I mean, what effect happens to the slow step? The slow step doesn't really have H2O2. So why is the slow step getting affected by H2O2? I mean, I'm saying that rate depends on H2O2 concentration. And the slow step, it doesn't really have H2O2. So why is the slow step increasing in speed because of H2O2? So you start tracing this. If you increase H2O2, IO minus 1 increases in concentration. If you increase IO minus 1 concentration, HY increases in concentration. And when HY increases in concentration, that means the slow step would speed up. Is this clear?
Yes, sir.
Okay, so there's an indirect dependence. That is, there was no H2O2 over here. And the rate of the reaction should not have depended on H2O2. But by increasing H2O2, you increase the concentration of IO minus 1. By increasing the concentration of IO minus 1, you ended up increasing the concentration of HY. And that's why the slow step speeds up. Adam, is this clear? It's because it's proportionality, right? It's when rate is dependent on H plus 1 and rate is again dependent on H plus 1, these terms, I mean, all of these terms are getting multiplied. So H plus 1 becomes squared because it's appearing twice in the expression. Is this clear?
Yes, sir.
And always remember, it's in proportionality, you're always multiplying things. Like it's rate is dependent on H plus 1 and the rate was again dependent on H plus 1. So it kind of becomes H plus 1 squared. I say anyways, so H2O2, it makes sense. Like if you increase H2O2, HOI increases and the slow step speeds up and the rate of reaction speeds up. So what happens when H plus 1, why does it, if I double the concentration of H plus 1, why does the reaction quadruple? Why does the speed increase by so much? So what happens when H plus 1, so let's focus on H plus 1. So you've got H plus 1 over here, right? You increase the concentration of H plus 1, the slow step would increase in speed, right? That's fine. That's going to be directly proportional. It should not be square. You increase the concentration, the collisions would double and the reaction would speed up. So that's just, it's speeding up 1 times, right? So why is it becoming square now? When you increase the concentration of H plus 1, another thing happens. Like H plus 1 is involved in the previous step as well. So if you increase the concentration of H plus 1, the concentration of HY would also increase. Like you've got more H plus 1. If you've got more H plus 1, there's going to be more HY that would be formed as well. So by increasing the concentration of H plus 1, what's happening is you're doubling the speed of the reaction twice. First, by increasing the concentration of H plus 1, the slow step speeds up. And because you've increased the concentration of H plus 1, the HY concentration also increases. And the reaction speeds up again. So it's affecting 2 of the reactants. This speeds up, the concentration becomes higher. And so that's why the reaction is quadrupling now. Is this point clear? Yes or no?
Yes, sir.
And the
Yes,
same,
sir.
and the same goes for I minus 1. And the same goes for I minus 1. Why is it quadrupling? Like if you double the concentration of I minus 1, why does the reaction increases by a higher amount? Like why does it quadruple? So this time you increase the I-1 concentration, so the slow step would speed up, right? That makes sense. It's involved in the slow step becomes faster. But if you increase the concentration of I-1 is involved in the previous steps as well. So by increasing I-1, IO-1 concentration would be higher. If IO-1 concentration is higher, then HOI concentration would be higher. So again, I-1 is also going to affect the concentration of HOI. So not only I-1 would speed up the reaction, there would be a higher concentration, there going to be more collisions. But because of I-1, IO-1, IO-1, HOI concentration would also be higher. And if its concentration is higher, then the reaction would again speed up. So that's why it's more sensitive to it. It's because it's affecting two of the reactants. And that's why the rate of the reaction is a lot more sensitive to H+1 and I-1. Is this clear?
Yes.
So remember, it's order 2 comes from mechanism. Order 2 comes from the fact that there would be some intermediate. So we can do some other example like this. If I can find, I mean, there was a 4-step mechanism. Just 1 second.
So is any step with intermediates a order 2 reaction, a type of order 2?
Hey, which one?
Is any like reaction that has an intermediate have order of 2?
Hey, remember, the intermediate doesn't have an order. You don't, I mean, it's always the initial reactants. The rate is only dependent on the initial reactants. I mean, if the slow step has intermediates, your task is to remove the intermediates. Like rate depends on HOI, right? So your task is to get rid of the intermediate in the rate equation. Like if I say rate depends on HOI, I mean, you're going to trace it back. You're going to say that a rate doesn't really depend on HOI. It's actually dependent on H+1 and IO-1. And then you figured out that it depends on IO-1. You're going to trace it back. Indirectly depends on I-1 and H2O2. Is this clear?
Yes.
So the order is not for the intermediates. I mean, if initially it involves an intermediate, you have to get rid of the intermediate. Is that clear?
Yes.
So there was just let me try and find just a second. There was a 4-step mechanism. So probably this one. I think this is kind of a similar reaction. So it's a 4-step mechanism. So what I'm going to try and do is I'm going to trace everything. Like let's say the last step is my slow step. So that means you just have to increase the slow step. That's all. The speed of the reaction depends on the slow step. So the rate depends on the concentration of OH-1 ions and on the concentration of H+1 ions, right? But start tracing them back. Like OH ions were produced in the previous step. The concentration of OH ion depends on I-1 and HIO. So I'm going to remove the OH ions. I'm going to say that the rate depends on I-1 and HIO. Is this clear? Right? Is this clear? But then I'm saying that rate depends on HIO. HIO itself is an intermediate. That means the rate of the reaction doesn't really depend on HIO. HIO itself depends on IO-1 and H+1 concentration. So it depends on H+1 concentration and it depends on IO-1 concentration, right? So I'm over here now. Now I'm saying that rate depends on IO-1 concentration, and I've figured out that IO-1 itself depends on I-1 and H2O2. So it depends on I-1 and H2O2. So if you sum all of them up, your rate actually depends on h plus 1 twice, so that's squared. It depends on I minus 1, so that is also squared because it's pairing twice, and H2O2 is a pairing just once. Okay, so it's kind of a similar reaction that we just did. Is this clear?
Yes, sir.
Okay, Bakio, is this clear?
Yes, sir.
Yes.
So now any step could be the slow step. I'm just assuming this is a slow step. So let's assume that some other step is the slow step. You're going to get a different rate equation or rate relationship. Let's say the second step is my slow step. So now the rate only depends on h plus 1 and all the rest are fast steps. So, I mean, increasing the speed of the fast step, that's pointless. Like changing the concentration of any other reactant is kind of meaningless. It's only the slow step that you have to increase in speed. So rate, if the second step is the slow step, then rate depends on h plus 1 and IO minus 1. And then you figure out that IO minus 1 is made in the previous step, and IO minus 1 itself depends on H2O2 and I minus 1. So you're getting different orders now. The orders are now 1 for H plus 1, there's 1 for H2O2, and the order is 1 for I minus 1. Over here, the order was 2. So it all depends which one is your slow step. So the order of the reaction depends on the slow step. Similarly, let's try and if there's another mechanism. So we've got this reaction now. And it's a 3-step mechanism. So let's say the second step is my slow step. So that means rate depends on these two things. And it depends on HClO. And then you figure out that HClO itself was made in the previous step. It depends on H2O and ClO minus 1. So when I say rate depends on HClO, it kind of indirectly depends on ClO minus 1 concentration, and it depends on H2O concentration. Right? Is this clear?
Yes.
So here, let's continue tomorrow. That's all. Tika, that's the first part. If you have the mechanism of the reaction, you can figure out the order of the reaction. You can figure out if it's order 0. Order 0 is when it's in the fast step. Order 1 would be if it's in the slow step. And order 2 would be, appear when you start tracing, like you give them first order based on the slow step, but when you start tracing them back, then the rate would be dependent many times on the same thing. So it would become order 2 or order 3, depending on that. So here, let's continue from here. Tomorrow we'll study the second technique of finding order of reaction. Okay, then everyone take care.
Thank you, sir.
Okay, Hafiz.